Hi, my name is Christopher Meyer, and this is Lab 3, Magnetic Field of a Bar Magnet. So in this lab, the purpose of the lab was to observe the relationship between a magnetic field and an observable distance, both on and off the magnetic field's axis. Further, it was also to further understand the Biot-Savart law, which we can see at the bottom right, and then also model the magnetic field computationally. A result from the lab was that the magnetic dipole found to be 7.553 amps times meters squared, and the N came out to be negative 2.5304. So the lab procedure, first we decide to determine the direction of magnetic north. By doing so, we would lie the phone flat on the table and rotate until the x component was 0 with the app. Then we would set up the meter stick orthogonal to north, and then locate the magnetometer of the phone by sliding the phone perpendicular to the meter stick in the x and y direction, and then marking the axes with an edge of tape. Then we move the foam at various distances along the meter stick, both on the axis and at a 45-degree angle, and record the magnetic field components into a spreadsheet. The physics models we used in this lab was the magnetic field, which was B, is a function of mu, which is the magnetic dipole, which is in the direction south to north pole, and r, which is the observation vector, which can be expressed in the Biot-Savart law, which we saw in the first slide. However, for the lab, we would assume that all the constants, except for r, would be constant. And we do this with the magnitude of the magnetic field expressed with a distance dependence, which we see up on the right, where we see it's equal to k r to the n. In this idea, we expect n to be negative 3, and our goal is to try to confirm this through the experiment. With our measurements, you can see on the left each of the different distances we found and each of the magnetic fields that are resulted from there, and with the spreadsheet itself, it would calculate averages. With these averages and then taking the natural logs of them, it would plot a plot where we have the natural log versus the natural log of r. Now, using this plot, we would begin to use our calculations using the distance-dependent magnitude of the magnetic field. We would use this logarithmic plot so that we have a straight slope and a y-intercept. The slope itself would be n, which would be negative 2.5304, and the y-intercept would be the natural log of k. Using the natural log of k, we would find k, and then since we now have n and k and r, we would solve for mu, where we'd set the distance-dependent magnetic field to the actual Biot-Savart law. And in the end, we would find mu to be 7.553 amps times meters squared. Next, we would go with the off-axis magnetic field measurements. In this case, we would position the phone a distance d perp in the x and y directions, then measure the magnetic field using the app, and making sure to correct the y component by subtracting the magnitude of the Earth's magnetic field that we found from earlier. With this average distance of perpendicular being 0.1943 meters, we came out to find an average magnetic field net magnitude to be 4.939 times 10 to the negative 5th Teslas. Now, comparing these two, this measured magnetic field to the computational magnetic field, we obviously see a difference. With the computational, we found a magnitude that was a little larger, such as 5, which was 5.75 times 10 to the negative 5th, and the vector magnetic field itself was only in the x and y directions. Obviously, this is more or less due to human error and experimenting and assumptions that we take in the experiment as well as in the computational model, which we aren't able to account for otherwise. Next, we would model the magnetic field in GlowScript. First, we would define the observation locations on the x and y, on the on-axis and perpendicular to the axis. Then we would calculate the magnetic field at each location due to the bar magnet, and then create a 3 arrow to represent the B, the magnetic field. Here you can see the GlowScript results, where the orange arrows are the on-axis magnetic fields, the blue are the perpendicular, and the purple is the 45-degree magnetic field. To the right, you can see all of our results, such as the mu magnitude, as well as each of the magnetic fields on axis and perpendicular, and at the 45-degree angle. Finally, a reflection question. What if you hadn't oriented your experiment to compensate for magnetic north and had instead laid out your meter stick at some intermediate angle with respect to Earth's magnetic field? How would your results have changed? Well, in this case, all of our magnetometer readings would be skewed in the direction of magnetic north, and therefore all of our values k, n, and mu would all be less accurate because we would not have accounted for Earth's magnetic field, which we know is there, and it will cause our results to become less accurate. Now, what if you were to stick two identical magnets together end to end and run the experiment again? How do you expect your measurements to differ? Now, we assume the direction of the magnetic field would be the same. Additionally, we would assume the length of the magnet would be minimal, or a minimal change, and therefore the magnitude of the magnetic field would be approximately doubled. Thank you, and that is all.